The technique is already in use today all over the world, in submarines. Inside a sub, ballast tanks, sealed off from the living quarters, can be alternately filled with water or air, changing the sub's weight and its buoyancy. The submerged floating tunnel would work the same way. But to make sure it doesn't pop to the surface, a series of tethers would anchor it to the bottom. If built here in Norway, a submerged floating tunnel would solve the traffic problem while preserving the region's natural beauty.
When you look at all the alternatives, the submerged floating tunnel becomes very interesting very quickly.
But like all revolutionary ideas, the submerged floating tunnel has run into public skepticism. Nobody, not even here in Norway, wants to be the first to commission the new tunnel design. The local government has postponed the project. But the engineers remain optimistic. They're convinced the technology will prove itself once given the chance. And what about in the Atlantic? Could a 3,000-mile tunnel actually float between New York and the United Kingdom? Walter Grants has worked with floating tunnel designs, and even he's a skeptic.
It would be a very impressive structure if you could see it underwater, running all the way from London to New York.
The critical problem, how to keep it in place. What would prevent such a long floating tunnel from, well, floating away? In some locations, it might be possible to build giant piers, like an underwater bridge. But not in the Atlantic. It would take thousands and thousands of towers, many of them miles high, hundreds of times higher than bridge piers anywhere. The piers themselves would be a larger construction project than the tunnel. Another option would be to support the tunnel from above. Huge floating pontoons might hold the tunnel in place from the surface. Just not here, where the pontoons would be subject to the violent weather conditions in the Atlantic. Worse yet, the Atlantic is home to the powerful Gulf Stream. Currents constantly moving 100 times as much water a day as the Nile, the Colorado, the Amazon, the Mississippi, and the Yangtze rivers combined. But there is another technology for supporting massively heavy floating objects at sea. And it's already in use. In offshore oil platforms. 100 miles off the coast of Norway in the North Sea, the Hydron oil platform sits smack in the middle of the Gulf Stream's forceful currents. It stayed in place for almost a decade. In the early 90s, the platform was built in a shipyard and floated whole out to sea. Earlier oil platforms had used solid concrete piers to keep them in place. Once finished, they couldn't be moved. So engineers decided to try a never-before-tested technique. To the underside of the platform, they attached 1,000-foot-long steel pipes, just long enough to reach the bottom, where powerful suction anchors were driven into the sea floor. As the anchors were driven in, water was sucked out, creating a vacuum seal. The anchors had to be strong enough to hold the 360,000-ton platform in place. And the platform can still be easily moved to a new location, simply by pulling up the anchors. The system relies on the same scientific principle as a pendulum, only upside down.
If you remember a grandfather clock, when the weight is up here, it is forced down by gravity. If you just reverse that and put a buoyant element on the top and anchor it to the Z-bottom, when the waves then come, it is pressed a little bit down into the water and buoyancy presses it up.
Since the hydrant platform proved that the technology worked, the technique has been adapted for other platforms, as well as for proposed floating tunnels. But could it be adapted to the transatlantic tunnel? Engineers believe the ideal depth for the tunnel would be about 150 feet. That's deep enough to avoid ship traffic, yet shallow enough to minimize pressure problems. Steel cable tethers, like the kind used in suspension bridges, would hold the tunnel in place. But with one important difference. The cables on a suspension bridge keep the roadbed up. The cables on the tunnel would be holding it down. They'd provide not only the strength to hold the tunnel in place, but also the tiniest degree of give. The tunnel would need to sway just a bit to absorb the energy of underwater currents, the inevitable collision with a large sea animal. Or perhaps even worse. So what is the most likely design for a transatlantic tunnel? Engineers now believe it would be built of 54,000 prefabricated individual sections. Each section would have an outer skin of stainless steel. Directly beneath the steel would be a layer of superbuoyant foam. Under the foam, another steel hull. And inside that, the tunnel's concrete interior. The interior would hold eastbound and westbound tracks, as well as a centrally located auxiliary track for emergencies. Above and below the tracks, service tubes would provide power, communications, and access for repair. And since the Atlantic is seismically active, the entire tunnel, along with its 100,000 tethering cables, would be monitored continuously by a massive geopositioning system. Any shift in the sea floor would trigger an automated system-wide retensioning of the cables. If ever built, the transatlantic tunnel would be the largest, most complex, most expensive construction project in history. It would take thousands of workers laboring for decades under some of the most extreme conditions anywhere on the planet, especially out at sea, where specialized teams would sink, attach, and tether the massive tunnel sections, all 54,000 of them. The first sections might be attached under New York Harbor, and the work would then move out into the Atlantic. Workers would live on board floating platforms, which would keep moving out to sea. Divers would help maneuver the sections during placement operations. But attaching the tethers to the sea floor would most likely need to be done by submersibles, since no diver could survive the pressure at those extreme depths. Engineers estimate the tunnel would consume the entire output of every steel mill in the world, working 24 hours a day for more than 1 year. Which of course raises one more staggering problem.
The cost of the transatlantic tunnel would be in the trillions, perhaps the tens of trillions of dollars. In fact, the cost of the tunnel would be in excess of the gross national product of a large number of countries.
You would need combined operation of government and private industry and public sympathy, thinking more optimistically about improving the terms of life on Earth.